Yes, the figure below shows a circuit containing a battery EMF 12 volt, two resistor, a light dependent resistor LDR, yeah, and a meter and switch S. The battery has negligible internal resistance. Okay, let's see the question here. When the switch S is open, so that the potential difference between the point X and Y equals to 7.2. Yes, 7.2 in XY, yeah, in XY when S is open. So if we find the current first here, current I equals to V divided by R, or V is 12.0 divided by, yes, R when the S is open, so the resistance only 2 between 8 and 12, yeah. So this is also series, so we can say like the one, yeah. So here equals to 12 divided by 20, so 6 divided by 10, yeah, 0.6 ampere. Yes, this is about current in this circuit, yeah, in this circuit. When they start from 12 volt and go here and then goes to X and then Y and throw with ampere meter here, yeah, and go back again. Yes, this is the current inside of this circuit, yeah, not to LDR because the switch is still open. Okay, now what about VEX here? VXY, sorry, XY. VXY as the, actually this is IR, yeah, that's I as the 0.6, then times with R is 12, so we have number is 7.2, yeah, 7.2, 7.2, yeah, 7.2 volt, yeah. Yes, as the same with the question is, yeah, they need to prove it, they need we to prove it, yeah, that X on X and Y is has voltage as the 7.2 volt. You can see here this is same thing with 7.2 volt, yeah. Can you hear me, Loisa, Rene, and Ilona? Hello, Loisa, Rene? Oh, Ronan, hello. Something here. Then we see other condition. Yeah. The switch S is now closed. Describe and explain the change to each of the following when the intensity of light falling on ladder is increased. Yeah. Okay. No. If light increase, the resistance of LDR also increase. Increase. And when 12 ohms have width. So followed by okay. Okay guys, I explain again about the effect of the ammeter reading when the resistance or when the switch S is open. Yeah, when the S switch is open, so they have on the 12 and LDR combination, parallel combination, they have decreases resistor. So we can say on the parallel resistor, yeah, if this is, let's say this is 12 ohm and this is, like, say, uh, 5 or something. If we calculate this combination of the resistor, so the combination of resistor, it will be going down, or this is, it will be decreases before then, yeah, before 12 ohm. So if this combination resistor is decreases, so the total resistor, it will be decreases also. And if we use the Ohm's law as the I equals to V over R, yeah, since V is same with before 12 ohm, R is decreases, so we can say I, it will be increases, increases, yes, correct, it will be increases, yeah. Okay, get it? Kok Sir gak dengar kalian ya? Oke. Where is okay? Loisa, where is Ilona? Six student. Oh, Ilona, Loisa, Rene, and Ronan. Okay. Okay, guys, continue again about others number, yeah. The potential difference across x, y. Okay. Okay. The potential difference in x, y, actually this is um, this is same, yeah. Wait, no. Which is no. Since ammeter reading uh, in SS in or resistor. No. So potential difference. Yes. Okay. Because ammeter reading increases, so potential different it will increases also, yeah. Because IR, yeah. So I think okay. Okay, guys, we continue to number 2. Figure 1 shows the thermistor and fixed resistor of 200 ohms, yeah, connected through a switch S to 24 volt DC supply of negligible internal resistance. The voltmeter across the fixed resistor has a very high resistance. Okay. When the switch S is closed, the voltmeter initially measures 8 volt. Okay, calculate the current in the circuit. Oh, this is back again to Ohm's law, yeah. That's Ohm's law. I as the V over R. So V as 24. Wait. Oh, we use V in here, yeah. Because when the switch S is closed, the voltmeter initially measured 8. So we can say this is 8, but in the resistance 200 ohms. So we get 0.04, yeah, 0.04 ampere. Or yeah, this is actually 40 milliampere, yeah, because if we multiplication with the 1000, yeah, ampere to milliampere is 1000, so we can say 0.04 times 1000 equals to 40 milliampere. Yes. Okay, this is number 2 on this video. No potential difference V1 across the thermistor. Okay. Yes. This is what we call as the potential divider. Yeah. We have 24 here and we have 8 here. So when the voltmeter measuring in 200 ohm as the 8, so we can say here on the thermistor, yeah, it's equals to 24 minus 8, yeah. The calculator. So here, yeah, thank you, sir. So V1, yeah, V1 as the, yes, 24 minus 8 4. Yes, we have 16 volt. Yes. If you to slide, pages maybe, nah, that one. So question I, the resistance R1 of the thermistor. Oh. After we get the voltage or potential difference in thermistor, we come back again, use the Ohm's law to find the resistance of thermistor, yeah. So we can say here the resistance of thermistor is V divided by I. Yes. V as the 16 volt divided by I. The I is same with current on the 200 ohms because this is in series, yeah. In series the current is same. in parallel, the voltage is same. Yeah, so we can say here this is actual 0.04 amperes. So we have resistance as the 400, yeah, 400 ohms. Yes, 16 divided by 0.04, yes, 400 ohms. Now the power dissipated in the thermistor. Uh, the power, if you remember when you were in grade 9, yeah, the power has formula. Power equals to vi. So V on the thermistor we have 16 volt, yeah, times with I on the resistor is 0.04, yeah. So we have number, yeah, 16 times with 0.04, yes, 0.64 watt it, yes. Okay, get it, guys? Rene, Loisa, and Ilona, Ronan. Okay, yes, yes. This is for number 2. Yeah. I'll wait you around 5 minutes to copy this explanation. Yeah, and I will back 5 minutes later. Okay, guys, we continue again to other numbers. Yeah, I repeat again, this is actually same with uh, formula before. Yeah, previous formula. This is about Ohm's law, about series and parallel. Yeah, series as the about the combination resistor, yeah, resistor combination and series, resistor combination and parallel. Also about law of the current and voltage in series and parallel. As it in series, yeah, current is constant, but in parallel, voltage is constant. Also, yeah, in series, potential is dividing, yeah, dividing by R actually, and on the parallel, current is dividing by like a junction, like a, apa ya kita sebut tuh cabang-cabang itu, like a branch. Yes. Okay, we continue to next number. Yes, number. Oh, we have still B and C. Oh, this is A. Oh, this is still A. Now about B and C. Yes. Let's try to solve this question. Yeah. B and C. If you have any question, let me know and ask me about that question. Okay. B. A few minutes after closing the switch S, the voltmeter reading has risen to a steady value of 12 volt. The value of fixed resistor remains at 200 ohms. Explain why the potential difference across the fixed resistors increases. Yes, because this is, yeah, this is actually a thermistor, yeah, depending by heat or temperature, yeah, temperature, yeah. When temperature increase, yeah, resistance will be decreases, yeah, decreases. And when the temperature, yeah, or actually this is room temperature, yeah, room temperature increases, yeah, the resistance of thermistor, yeah, will be decreases. Wait. When the room temperature increases, the resistor of the will be, wait. Thermistor depends by depend depends by temperature. Yeah. When temperature increase, resistance will be decreases. When temperature will be decreases. Yes. Okay. So when we say the fixed resistor has increases, yeah, so the potential difference across the fixed resistors has increases. So it's actually the room temperature is decreases here, because this is increases. Okay. Now the resistance of the thermistor must now be 200. Let me see about diagram first. E4. Yes, I think this is about to compare, yeah, to compare with the resistor plus ohm. Yeah, it's like supposed to be same or less than 2 ohm. Yes, I think this is uh, because there is no thermistor has a value or has a number of resistance more than the weight more than of the resistor external, yeah, external. It's because thermistors like the sensor, like the, yes, sensor, not as the real thermistor. Sorry, thermistor, it's like as the sensor, not as the real resistor. So the maximum uh, resistance of this thermistor, it must be same or less than of the resistor external, or we call it, this is a resistor when resistor is 200 ohms, yeah. Okay, continue to see. Sketch on the left X figure 2 below a possible IV characteristics for the fixed resistor R, yeah, fixed resistor number R and thermistor number T. Okay, when R, yeah, fixed resistor, yeah, fixed resistor, wait, I use here, yes, resistor is V over I, so when we use 12 ohm, yeah, so we can say the current is to be, it's supposed to be um, wait, uh, see 12 divided by 200, so 12 divided by 200, 0.06, so we can say here, yes, this is the resistance, yeah. This is fixed resistance. This is for R. So what about thermistor T? The thermistor is less than of the R. We see on the current is uh, we already counted, yeah, about current is 0.04, so we can say here, yes, actually until here, yeah, or we can say, yes, oh, yes, oh, sorry, yes, this is the T1 and this is the R1. Why use this one? Yes, let me see it, but when the 12 ohm, they have ampere 0.06, yeah, of the fixed resistor, and for the thermistor when they has 8 volts, yeah, they in, oh sorry, Yes, actually the thermistor um you see here, yeah, 12 that is 12 volt, and then it's 10 ohm. Oh, V over I as the, I think here, yeah. Why graphic like that? Because the thermistor is less than of the fixed resistor. So we see about the graph is on the xy as the voltage, and on the y is the as the current. So V over R is the constant, yeah, constant number, uh, because T has less than of the R, so we can say the graph is going up, yeah, going up, because this is V over I, yeah, V over I. To be get number, small number, so like the graph need to go up, yeah, the one. Please copy this answer, and I will wait around 5 minutes to continue other question, yeah. Okay guys, we continue again to other number. Yeah, we see in, oh, this one, number 3. The figure below shows the potential divider circuit used to monitor of the temperature of a greenhouse. The thermistor T is a negative temperature coefficient type. Yes, the voltmeter is placed across the resistor R. Explain how the voltmeter reading changes as the temperature of the greenhouse increases. Wow. See this one, yeah, this is the thermistor is a negative temperature coefficient type. So if we say about negative temperature, so like this is opposite with the increases of temperature. Negative means if increase in temperature, that will be decrease in resistance. Yeah. This is can say increase it temperature, it will make decrease in resistance of Thermistor. So the question is they want, yeah, describe and explain how voltmeter reading changes as the temperature of the greenhouse increases. Yes, because resistance in, sorry, yes, because resistance of thermistor decreases, so the total resistor equals to decreases also. When the total resistor in this, I try to put, so it makes total resistance on the circuit, yeah, it will be decreases, yeah. And and current, yeah, it will be increased, yeah, because the total resistance decrease, yeah, increase. So when the current is increases, so when the current is increases, yeah, voltmeter as the V, yeah, increases also, yeah. Actually this is about the Ohm's law, back to Ohm's law, yeah, Ohm's law. V equals to IR. When yes, when current increase, yes, volt also it will be increase, yeah, on this voltmeter reading, yeah, not volt, not potential volt in here, but voltmeter reading here. Ooh, only, oh, number two. Number four, yes, number four, a battery of EMF E and internal resistance R deliver a current I to circuit of resistance R. Write down the equals E in terms of R, I, and R. Oh, this is about actually about Ohm's law, yeah. When we know about V as the E, yeah, equals to I, and then R as the total resistance, fixed resistor, and uh, internal resistance, yeah, R small. Yes, like that one. Okay, B, a flat car battery of internal resistance 0.06 ohm is to be changed using a battery charger have an EMF of 14 volt and internal resistance of 0.74 ohm as shown in the figure below. Yes, you can see the battery to be charged has its positive terminal connected to positive terminal of battery charger. Yeah. At the beginning of the charging process, the EMF of the flat car battery is 7.6 volt. So, for the circuit figure above, determine the total resistance. Whoa, yeah, just this is 0.74 plus 0.06, yeah. Uh, Here as the 0.74 plus 0.06, yes, equals to 0.8, yes, ohms, yeah, because this is series, yeah, this is series circuit. So the sum of EMF in the circuit, let me see about this one. This is polarity positive and this is negative. When they go to this is current, yeah, current here, and then they like collide with the positive also. So this is minus, yeah, not as the positive like this one. This is actually the EMF is 14, yeah, minus, yeah, 7.6 volt. So we can say here as the 4.4, yeah, 4.4 volt. Why not plus? Because the polarity is not continue with like this is plus and it's supposed to be negative plus negative plus and so on and so on. But in here the case is positive positive negative negative. So we can say this is minus, yeah, 14 minus 7.6 volt. State Kirchhoff's second law. Oh, this is the material not yet I explain to you, yeah. Later I will explain to you in A level, but this is actually for AS level, yeah. AS level or A level actually there is about the Kirchhoff law, yeah. So later I will explain more about the sum of law in the DC circuit. Okay, let's copy this answer. Oh, this is already 11:30, yeah. Okay guys, I think we will continue. Oh, maybe next month, yeah. Kan next week and next 2 weeks you have some of you, tapi ya some of you have semester to test, ya. Okay guys, maybe I want to chat you